This video will cover section 7.7, growth and decay, which is an application for exponential functions that we learned in section 7.6. So let's remember what the equation was for exponential functions. So y equals a times b to the x. Remember that a was talking about the y-intercept and b was the ratio. Now when we're talking about application problems or word problems, the a is the y-intercept, but for a word problem, let's talk about that y-intercept as being what we call the initial value. Because remember that the y-intercept is when x is 0, so the initial value would be when I'm starting out something. Okay, so the initial value, that's going to be in the a spot. Then the b is still going to be our ratio, or in word problems a lot of times we talk about it as a rate. And if that b is a fraction, so that is if b is between 0 and 1, then we are going to have what we call exponential decay. So if that's a fraction, that means I'm going to keep having something. So if I keep having something, it's going to get smaller and smaller and smaller, therefore it's called a decay. And then if that b is bigger than 1, then we're going to have growth. So if I keep multiplying by 2 or multiplying by 3, then you get bigger and bigger and bigger, and you have exponential growth. You've probably seen problems like this before in science, so like for bacteria. For bacteria, if I put bacteria in a petri dish and I allow it to grow, it's going to grow exponentially. So let's say if I have one cell that divides into 2, and those divide into 2, and those divide into 2, that's exponential growth. But exponential decay is, let's say you have a bacteria inside of your body, so like a virus or something like that. Then once your body starts fighting that, and so that's going to decay those bacteria cells within you. So then you would have a rate of fraction. Okay, I've just drawn a couple of graphs for you. So on the left side, we have growth. So that's, again, if your b, your base, is greater than 1. So you can see that my curve, my exponential curve, is curving up. So that's when you have exponential growth. Then on the right side, we have decay. So if b is a fraction, so between 0 and 1, then our exponential curve is going down. So you model decay. All right, so let's just look at a couple of examples. And so we have a word problem modeling some type of situation that has exponential growth and decay. And all we're going to do is write the equation for this situation. So remember with these models, we have an exponential. So we're going to model y equals a times b to the x, where a is the initial value and b is the rate. So number 1 is at an initial time. So right there, I'm going to pause and I'm going to think, okay, initial. I saw that word back up in the beginning for a being the initial value. So at the initial time, a sample contains 200 bacteria. So that right there, I know is my a value. That's my initial value. And the number triples every hour. So that triple right there represents a rate. So that's going to be my b. So if I'm tripling, I'm multiplying by 3. Then, instead of y and x, typically in a word problem, we're going to have different variables. So they represent those by t representing time, and b represents bacteria. Then we want to write the equation relating b and t. So we have b is what we're trying to find my bacteria. So that's going to be like the y. So b equals, and then the a times the small b to the t. So a is 200 times little b is 3, and then to my exponent of t. If you wanted to write that out using like y and x to begin with, if those b and t's get confusing, then you know a and b is 203, so you could have said y equals 200 times 3 to the x, and then you could figure out that b represents the y and t represents the x. And that's it, that's the equation. So bacteria growth and decay is pretty easy problem to write the equation of. So number 2 is a little bit trickier. We have a percent problem. So when we have a percent problem, it's either going to be a percent increase, so that's like a growth problem, or a percent decrease. So you have to figure out what kind that is. So for number 2, it says at an initial time again, a deposit of $300 was made. So that value right there is our initial amount, so that's going to be our A. Into an account that earned 4% interest. So you got to be careful there. You see the earned. Earning money is positive money. So I'm adding 4% interest at the end of the year. Let T represent time in years, and A represents the number of dollars in the account at time T, where T equals 0 is initial time. Write an equation relating A and T. Use the equation to then calculate the number of dollars in the account after 10 years. So we're not only going to find the equation, then we're going to use the equation to actually find out a certain amount of money. Now, our A, I told you, we found to be 300. However, the B is not 4%. It's a 4% increase. Okay, and actually I shouldn't even say B there. I should say that my rate is a 4% increase. So the actual value that we're going to put into B is still not 0.04, because 4% is 0.04. But again, that's a 0.04%, or a 0.04 increase. So if I have a 4% increase, what that means is I'm adding that increase on to 100%. Because if I'm earning interest, I'm getting 100% of my money back plus 4%. So my number needs to be bigger. If I use 0.4 or 0.04 as my rate, I'm only getting 4% of my money back, and I'm not getting the original 300. So my B actually is that 100% plus 0.04. And actually, sorry, that 100% in that second one, if I make that as a decimal, 100% is just like adding 1. So that B is 1 plus 0.04. So 1.04 is like 104%. All right, so I'm going to put that kind of in parentheses here. So a 4% increase is 104%, which as a decimal is 1.04. Okay, and as that was a decrease, let's say it was a credit card bill that took off 4%, then you would subtract 4% from 100. That would be 96%. Keep that in mind. All right, so now we have our A and our B. And so to write the equation, we have A is the number in our amount, or in our account, and then the initial amount, 300, times our rate is 1.04 to the exponent is time here. So this is my equation. All right, then they ask us to use that equation to calculate the number of the dollars in the amount after 10 years. 10 is a year, so that's a time. So now using my equation, we're going to plug 10 in for T and then see what you get. And you're going to have to probably use a calculator for this. So this is 300 times 1.04 to the 10th power. Which, if you put that into a calculator, you would get about $444 and a little bit of change. I think it's like 70 cents. So you got the $300 that you put in, plus an initial about $144 to get you this total amount of money. Okay? So that's growth and decay, which is a application of exponential